Hello friends, welcome to Engineering Funda family. In this video, I'm going to solve three very interesting examples based on generation and recombination using uniform illumination. In my last video, I have explained you theory based on this. By this theory, you will be able to understand how these formulas are coming. So I request you to go through my last video. By using these formulas, I'll be solving three questions. Before I start with solutions, what I want is you just solve these questions by your own first. Later you can check for the solution over here. So this is first question. You can pause the video in between. This is second question. This is third question. So that is how three questions are there. I hope you might have paused the video in between and you might have tried these questions by your own. Now I'm going to solve first question over here. So if you observe first question, see in first question, consider silicon sample at T is equals to 300 Kelvin. So let me note down the data. Temperature is given with a uniform donor density Nd, that is pi into 10 to the power 16 per centimeter cube. So donor density is given, means here we are having N-type material. Illuminated uniformly such that optical generation rate, that is also given. Optical generation rate, that is 1.5 into 10 to the power 20 per centimeter cube per second throughout the sample. The incident radiation is turned off at T is equals to 0. So we are turning off this light at T is equals to 0. Assume low level injection to be valid and ignore surface effect. So here we are discussing about low level injection that should be valid, means we will be calculating things for minority carriers only, right? The carrier lifetimes are Tp, that is 0.1 microsecond, and Tn, that is 0.5 microsecond. The whole concentration at T is equals to 0 and at T is equals to 0.3 microsecond are. So we are deal with to find whole concentration, right? And that is what the case which we have seen it in my last video of theory. You can observe here I have discussed about N-type material only, in which minority carriers are holes. So we were been calculating minority carriers before T is equals to 0 and after T is equals to 0 as per this expression, right? So that is what the case which we will be using over here for solution of this problem. So here let us solve this step by step. So first question is what? Concentration of hole at T is equals to 0. How to identify that? See, that is quite simple. Delta P is equals to generation into lifetime of holes, as we are talking about holes over here, right? So generation, optical generation is 1.5 into 10 to the power 16 into lifetime of holes. So lifetime of holes, that is 1.1 microsecond, right? So 0.1 microsecond, and here optical generation, that is 10 to the power 20 over here. So if you multiply this 1.5 into 10 to the power, see 20 minus 1 19 minus 6 13. So 10 to the power 13 per centimeter cube, that will be this delta P. So if you observe ABCD, these two options are false, that you can say. Now we need to find whole concentration at T is equals to 0.3 microsecond. So that even we can calculate. In my last video I have explained that, right? You see, this P is equals to P naught plus delta P into e to the power minus T by tau P, right? So that is what the basic formula that we'll be using over here. P is equals to P naught plus delta P into e to the power minus T by tau P, where this P naught, that we need to ignore. Why? The reason is it is small, right? So we will be ignoring this as we are discussing about N-type material, right? With which we are discussing about light illumination. So temperature dependent things that we will be ignoring over here. So we will be calculating this based on delta P into e to the power minus T by tau P. So here let us substitute the values. Delta P that we have calculated 1.5 into 10 to the power 13 into e to the power minus T, where T is 0.3 microsecond. So let us say 0.3 divided by tau P, and tau P is 0.1 microsecond. So you can say this is 1.5 into 10 to the power 13 into e to the power minus 3. And if you solve this in calculator, let me check what is my answer. So my answer is 7.47 into 10 to the power 11 per centimeter cube. So if you observe this, this is our correct option, right? So that is how simply we can solve the question. But first you need to understand how basic fundamentals are there. Let us solve second interesting question now. So in second question, what is given? An n-type silicon sample is uniformly illuminated with light which generates 10 to the power 20 electrons per electron hole pair per centimeter cube per second. So here generation rate that is given. So let me note down the data. Generation rate that is 10 to the power 20 that is given per centimeter cube per second, right? That is how it is given. The minority carrier lifetime in the sample is 1 microsecond. So minority carrier. So here n-type silicon is there. So minority carrier will be holes. So tau p that is given, that is 1 microsecond, means 10 to the power minus 6 second, right? In steady state, hole concentration in sample is approximately 10 to the power x, where x is integer, value of x is. So here in steady state, we need to find what is the value of this x. So here, as we have discussed, what is the basic calculation? Delta P, which is what? Concentration generation due to light. And that is how much? Generation rate into tau p. Here generation rate is 10 to the power 20. Tau p is 10 to the power minus 6. If you solve this, this will be 10 to the power 14, right? And if you observe here, that is given over here, that is 10 to the power x. So if it is 10 to the power x, then you can say x over here, that is 14. So our answer over here, that will be 14 over here, which is x, right? So that is how simply we can solve the questions. First you need to understand what is given over here, right? Let us solve third question over here. So in third question, a thin p-type silicon sample is uniformly illuminated with light which generates axis carriers. So we have seen, right, like as you fall light uniformly, then it will be generating electron hole pairs over here, and that is referred as axis carriers, which we have seen it as per delta P in case of n-type material, and that is delta N in case of p-type material, right? The recombination rate is directly proportional to. So here question is, what is recombination rate? I have explained that. See, what is recombination rate? You see, I have explained that, right? For n-type, recombination rate is P minus P naught by tau p. In case of p-type material, it will be n minus n naught by tau p. So that is the basic formula for it. So recombination rate, that is for p-type, it will be n minus n naught by tau n, right? So here question is, you see, recombination rate is directly proportional to minority carrier mobility. No, it is not proportional to minority carrier mobility. Minority carrier recombination lifetime. No, it is not proportional to that. It is inversely proportional to it, that you can say. The majority carrier concentration. No, it is not depending on majority carrier concentration. The axis minority carrier concentration. Yes, you see this N, that is axis minority carrier concentration, which is happening because of uniformly illuminated light on this material, right? So you can say this R that is proportional to this difference, right? That difference itself explains it is proportional to generated concentration, right? So this is what delta N, that you can say, which is what axis carriers due to light over here, right? So that is how we can solve this type of questions. I hope you have understood this. Still, if anything that you would like to share, please note it down in comment section. I'll be happy to help you. Thank you so much for watching this video.